Welcome back to Lesson 7 of our Number Theory Explainer. Today, we are seriously upgrading our logical integer sandbox toolkit. If you've been with us, you already know number theory is often called the queen of mathematics. We've been poking at the DNA of numbers using nothing but integers and finding these crazy deep patterns hiding inside what looks like a simple number line. So today, let's take one of our absolutely foundational tools, mathematical induction, and give it a massive power-up together. Let's get into it.
So to understand why we need this upgrade, we kind of have to look at a limitation in our current toolkit. You remember we talked about standard mathematical induction as domino math, right? You knock down the first domino, prove that any falling domino will knock over the one immediately next to it, and boom, you've proven an infinite chain of truths. But ask yourself this, what if one domino just isn't heavy enough to knock over the next? How do we prove an infinite chain when the immediate previous step doesn't give us enough force? Like, what if step k actually has nothing to do with step k plus 1?
Well, this perfectly illustrates our solution. On the left, we have regular induction. You assume a statement is true for some arbitrary integer k, and you use that single solitary fact to prove it for k plus 1. But on the right, we have strong induction. Instead of just relying on that one single domino right behind your target, strong induction uses the combined massive weight of all previous dominoes. We're talking every integer from 2 all the way up to k, all working together to knock down the next one. It's literally like having an entire wall of dominoes collectively pushing on the next one in line.
Which brings us to the prime factorization challenge.
This is our massive mathematical mountain for today, first mapped out by Carl Friedrich Gauss back in 1801. The fundamental theorem of arithmetic. Specifically, we're tackling the existence half of this theorem. It states that every natural number greater than 1 can be expressed as a product of prime numbers. You know primes, those numbers strictly greater than 1 with no divisors other than 1 and themselves. They are the essential elemental building blocks for all natural numbers. So our goal in this explainer is to mathematically prove that every single composite number out there can be broken down into these prime blocks.
You might be wondering, why do we actually need strong induction for this? Well, regular induction completely fails us here. Imagine we're trying to prove that 15 can be factored into primes. With regular induction, we'd only be allowed to look at the number immediately preceding it, 14. But knowing that 14 factors into 2 times 7, that doesn't magically help you figure out the factors of 15. The immediate step-by-step chain is completely broken because the prime factors of a number are smaller, but they aren't necessarily exactly one step smaller. To factor 15, we need to reach back to 3 and 5. We need access to the entire history of our integers.
To pull this off correctly, we need a clear structure. Here is our 3-step roadmap for the proof we're about to execute. First, the base case. Second, the strong inductive hypothesis. And finally, the inductive step.
Let's start right at the beginning with the base step.
This is where we flick our very first domino to start the chain reaction. Because our theorem applies to every natural number strictly greater than 1, our starting point in the integer sandbox has to be the number 2. And honestly, what's really beautiful here is how incredibly simple this first step is. The number 2 is, by definition, a prime number. Because of that, it is its own prime factorization. The statement holds true immediately. Our base case is totally solid, and we've successfully knocked down domino number 1.
Moving right along to step 2, the strong inductive hypothesis.
I actually pulled this exact phrasing directly from a formal mathematical text, The Architecture of Higher Arithmetic. It says, assume the hypothesis holds for all integers I, such that I is between 2 and k, inclusive. This right here, this is the absolute core of strong induction. We are assuming our statement that a number can be written as a product of primes is completely true for every single integer starting from 2 all the way up to some arbitrary number k. We are building a massive, unbroken block of truth to work with.
Now for the climax, smashing the next domino.
This is where the magic happens. To keep our logic completely airtight for the very next integer, which we'll call k plus 1, we have to split the possibilities. Our target integer absolutely must fall into one of 2 distinct categories. It is either a prime number itself or its composite, meaning not prime. In our integer universe, there are literally no other options.
Let's look at that first possibility. If k plus 1 happens to be prime, well, the proof is instantly satisfied. Just like our base case with the number 2, a prime number is already its own prime factorization. If that's the case, the domino falls with 0 effort and we are done.
But, as mathematicians, we can't just hope for the easy route. We have to account for the harder path.
So what if k plus 1 is composite? By definition, a composite number can be broken down. It has some divisor, let's call it a, that sits strictly between 1 and k plus 1. Because a is a divisor, we can split k plus 1 into two smaller integers, a and b, meaning k plus 1 equals a times b. And crucially, both a and b have to be greater than 1, but strictly less than k plus 1.
Now get ready, because here's the mind-blowing aha moment. Because a and b are strictly less than k plus 1, that means they are less than or equal to k, which means they fall perfectly inside our strong inductive hypothesis. Remember that giant block of dominoes we assumed were true? Because we assumed the theorem worked for all previous numbers up to k, we are 100% guaranteed that our smaller integers a and b already have prime factorizations.
Because of that ironclad guarantee, we can simply represent a and b as their respective products of primes. We can write a as a string of primes multiplied together. Let's call them p1 through pu. And we do the exact same for b, as another string of primes, q1 through qv. We don't even need to know what those specific primes actually are. We just know for an absolute fact that they exist.
Let's see how this builds to our grand conclusion. By simple substitution, if k plus 1 equals a times b, we just swap our prime strings back in. Multiplying those smaller prime factors back together gives us one massive, valid product of primes for k plus 1. We literally just used the prime factorization of smaller, older dominoes to successfully smash the k plus 1 domino.
And that perfectly demonstrates the power of strong induction.
Let's read the final formal conclusion from our sources to fully appreciate what we just pulled off. Hence, in all cases, k plus 1 can be factored into primes. Thus, by the principle of strong induction, a prime factorization exists for all integers n strictly greater than 1. We just proved a massive, foundational pillar of mathematics using nothing but pure logic. How cool is that?
But hold on before you get too comfortable. We aren't completely done with the fundamental theorem of arithmetic. We've proven the existence half. We know for sure that prime factorizations exist for every single integer. But are they absolutely unique? Like, could a number have two completely different sets of prime factors? That is the next massive mystery of the theorem, and we're going to use a brilliant tool called Euclid's lemma to crack it in our next explainer. You definitely won't want to miss it. Thanks for exploring the sandbox with me today.